Hello, am I audible? Hello, can you guys hear me?
Yeah, you're audible.
There seems to be some sort of echo. Let me see. So you can hear my voice clearly, right, from your end, or is there some echo? Are you able to hear me clearly, or am I the only one who is hearing my voice echo back to me?
Yeah, there is an echo actually.
Okay, just a sec. Now is it fine?
No, man of the echo is still there.
Okay.
But I think we can get started. That's okay.
Okay, maybe what I can do is I can try and mute my laptop and see if it's echo is still there if I uh, unmute my device mic. Oh, hello.
Yeah, better now, I think.
You can hear me, right?
Yes.
Okay. Hi guys. So sorry for the delay. I hope there is no echo now. So I'll begin. So this is a new semester for the NPTEL courses. So I'll be one of your TA for the reinforcement learning course. So this is being taken by Professor Ravindran Balaraman. So we are a group of three people, including me. So I am assigned to take the interaction session every Friday from 6 to 8 p.m. And Saturday and Sunday, there are two other TAs who will take the respective sessions. Okay. And we all of us are taking the courses independently. So you might expect some sort of overlap when we start teaching in the coursework. So just keep that in mind. So today my focus is mainly on the stuff that has been covered in week one. So it's kind of a discussion session. If you have any questions, if you have any queries, you feel free to unmute at any time and ask me about any conceptual clarity that you require. Otherwise, what I have planned is I'll quickly just do a recap of what all has been covered in week one and provide some more insights from my own end on the introductory part of reinforcement learning. And towards the end, maybe we can try look at the practice assignment questions that has been covered in week one, and also there has been some questions that were given in the week zero practice assignment. Maybe we take a look at that once we pass the 1 hour mark. Okay, so since this is a 2 hour session, so I don't expect to continuously speak for 2 hours. Uh, so it's better if we have some sort of an interaction, some sort of a dialogue between us, so that we keep the session running. Okay. So moving on. So the first thing is I introduce myself. So my name is Manav Mishra. I am a third year PhD student in the ECS department at ISR Bhopal. So, my research interest is mainly in the area of multi-agent reinforcement learning. So, I typically work with multi-agent robotic systems and also on swarm robotics. So, if you guys have any interest in that field and you're working on that area, you might reach out to me. We can discuss anytime whatever you want to discuss about my research topic. And so, this is basically a lecture series as part of the NPTEL program, and uh, I'm one of the TA, and we'll have weekly sessions every Friday from 6 to 8 p.m. Okay, so moving ahead. Okay, so the first question that comes up is what is RL? RL, what is reinforcement learning from an intuition perspective? Okay, so if you look at the definition, reinforcement learning is basically an optimization problem. What it deals with is basically how we formulate models that learns to perform certain behaviors or certain tasks by means of repeated interactions with some entity. Okay, so here the entity is termed as the environment, and the person who performed the act is termed as the agent. So reinforcement learning is basically a means of interaction between the agent and the environment, and through this repeated interaction, we expect the agent to learn some complex behavior or some complex task, we and deploy it on a real world system. Okay, so it uses some sort of a reward to tell the agent if the task is being performed correctly or not. So that all has been covered in the lectures previously. So the idea behind reinforcement learning, the basic concept, if we look at it from a historical standpoint, it comes from behavioral psychology. Okay, so you might have heard of the experiment called the Pavlov's dog experiment. So what happens is every time the owner gives before giving food to the dog, he rings a bell. So over time, with repeated number of iterations, the dog learns to associate the sound of the bell to basically it expects food after that. So it starts salivating in anticipation to the sound of the bell. So this form of association based learning is something that reinforcement learning deals with. Okay. So it is about taking some suitable actions, some suitable responses to maximize the reward in a particular situation. So here the association that reinforcement learning deals with is basically the association between states and actions. So state is the variable that the agent has access to at time t, and based on the state that is available to the agent at a particular time instance, the agent learns to associate a action that maximizes its satisfaction or maximizes its payoff. Okay, so RL can be in a way considered to be as a science of decision making. Okay, again, if you look at it from behavioral psychological uh, point of view, so it's think of it as the art of habit forming. Okay, so let's say you want to build a new habit. Okay, so the way you decide on something to do is first you have something known as an environmental cue. Okay, so a cue is something that is what we call state in reinforcement learning, but cue is something that triggers some sort of triggers some sort of action from the user. Okay, so the queue is basically the beginning, what triggers, what leads to some response from the user, and based on the queue that is available in the environment, the user takes a response, and based on the response, the user gets a payoff or a reward. So this reward is basically means of satisfaction that they receive on taking that particular action, and this continues on repeating until a certain habit or a certain behavior is learned. Okay, so this is the intuitive perspective of reinforcement learning. So next up, coming to the actual definition. So reinforcement learning is basically, like I said, it's a means of interaction between the agent and the environment. So the agent takes an environment that makes some changes in the takes an action which makes some changes in the environment. So the environment updates the agent with the state that the agent receives because of the change that the agent made in the environment, and based on that, the agent takes an action, and the action is evaluated by the environment by means of an evaluation function. Here we call it as a reward function. So in reinforcement learning, we typically learn from the close interaction of an agent with the environment. The environment around us is not deterministic, it is stochastic in nature. There is some sort of a noisy, delayed scalar evaluation that is coming from the environment. So that is to basically optimize the behavior that the agent is trying to learn or trying to mimic. And eventually, what we want to do is we want to maximize the measure of long-term performance in the entire system, right? So this is the basics of reinforcement learning. So let me just give you a quick real life example so you might understand why exactly we need a reinforcement learning and what do we mean by a stochastic environment. Okay, so imagine that you have moved to a new city. Okay, and you are basically trying to explore different food places. So let's say there are around 5 to 6 restaurants that you want to visit and try to eat food and figure out which restaurant suits you better, and you want to basically come up with a favorite restaurant. Okay, so typically what happens is you go to restaurant one, you eat the food there, you get some satisfaction. So next day you go to restaurant two, or you again go to restaurant one. So you over a period of time you eventually end up going to all the restaurants some k number of times. Okay, now the stochasticity here comes in is that sometimes it might happen that the satisfaction that you received on going to restaurant one on day one and the satisfaction that you receive on going to restaurant day two may vary. Okay, so the variance here can be from the agent perspective. Suppose you might have a hard day or long day, so you're more hungry. So on day one, your satisfaction was more compared to day two, and subsequently, over a period of time, you learn to average all these rewards and come up with an estimate which restaurant is better and which restaurant should I continue keep on going continuously. Okay, so there is some sort of a distribution of the payoff or the satisfaction that the user gets. So this is from the user perspective. Sometimes it may happen that due to the difference in weather, some food style might suit you more, or some different kind of food will suit you better, or sometimes you might be ill, or sometimes you might not feel like eating at all. So those factors come into picture. Sometimes it may happen that the restaurant has an off day. Okay, the cook doesn't cook the food the way they have been cooking since a lot of years. Sometimes there is a lot of crowd, so the service is an issue. So all these factors come into picture. So this is where the stochastics come in. So that's why we have a noisy stochastic environment, and the scalar evaluation is also noisy and is delayed over time. So the thing here is that the evaluation that you get is after the task is performed. Okay. So after you have eaten the food, you get a measure of satisfaction, and from there you move on. But typically, what happens in most of the RL problems is that sometimes to get any sort of evaluation, or sometimes to get any sort of reward function, you might need to perform a sequence of actions in a particular order before you end up reaching to that reward. Okay, so typically what happens is the reward is not immediate. For every small micro action that you take, you might not get the reward. You might be required to take a sequence of actions over a period of time to end up getting a reward. Okay, so like professor mentions in the class lectures, so suppose you're playing a game of chess. Okay, so the reward that you get is only after the game of chess has ended. Okay, but that need not associate the last move that you made to be the cause of winning. Okay, so it might happen that you might have made some good decisions, some 20, 25 moves back, which resulted in your victory. So that association is typically an issue. So which move do you assign more credit to, or which move do you assign less credit to? So this is in the example of chess. Okay. Similarly, let's say you're again not restaurant example, maybe some other example where this delayed reward comes into picture. Can anyone come up with some example where you might find some delayed reward kind of a setup? One thing I mentioned was the game of chess. Okay, so only after you win, you get some sort of a reward. Any other real life kind of an example, which may not necessarily be any game or something like that?
The long-term investments which we do.
Yeah, okay. That is one way to look at it. So let's say you are an investor and you have a long-term kind of a horizon. So the small aberrations don't make some sort of a difference, but over let's say a 10, 15 period of time, you might see some reward. Okay, but still the reward is immediate for each trade you make. For each trade you make, you get okay. You don't get the immediate reward. Maybe you get it after some time period of time. So okay, that's one example. Or something like, let's say you want to move from let's say city A to city B. Okay, so you want to catch a flight. Okay, so to catch a flight, you might need to perform a sequence of steps. You might need to get out of the room, you might have to take a taxi, you might have to carry your luggage, do all the security check-in, actually sit in the flight, and then reach the destination. So the reward you will get only after I've moved from city A to city B. So all the micro level actions don't end up getting rewarded. Okay, so there is some kind of a sparsity that is happening with these kind of rewards. Okay, so this is basically what we mean by a delayed reward. So what happens in a delayed reward is there is okay, let me write it down. So your delayed reward is a sparse reward kind of a setup, right? What it ends up kind of creates a temporal disconnect between uh, okay. So this problem of reward assignment or credit assignment is a prevalent problem in reinforcement learning. The idea of coming up with an apt reward function that necessarily maximizes the action that I have taken to the states that I have visited is something that is uh, kind of a how do I say it? Some kind of an ad hoc approach that people use nowadays. But yeah, so this is an important pending problem. So typically, what people do is instead of having uh, a reward that a person receives at the end of the entire task being done, they end up employing something known as reward shaping. So what happens in reward shaping is you typically kind of assign some smaller rewards to the micro actions that you have been taking so far. But again, the weightage that you might need to give to each and every micro action, that also becomes a challenging task in itself. Okay, so this is the issue with one of the major issue on defining the reward function in a reinforcement learning kind of a setup. Okay, so eventually what we end up doing is because of okay, so because of the stochastic environment that we have here, okay, so we don't end up learning some sort of a deterministic function that maps from the state to action, but rather the mapping from state to action is probabilistic, so it ends up giving rise to some sort of a policy or some sort of behavior that the agent ends up learning in RL. Okay, so you understand that this is some sort of a trial and error kind of a learning. So that trial and error happens through repeated interaction between the agent and the environment. Okay. Right. So next up, I'll quickly explain few terminologies that people use in reinforcement learning. So RL can be broken down into four components broadly. Okay, there might be several more components, but these are the four major components that constitute uh, an RL problem. So I'll quickly read through each of them and maybe introduce them to you slowly. Okay, so we start with the first component. The first component is known as the policy. Okay, so policy is basically a rule used by an agent to determine what actions to take. Or this is some kind of a mapping that happens between a state and an environment. Okay, so the mapping here is known as the policy. Here it defines the learning agent's way of behaving at a given time. Yeah, like I said, it's a mapping from perceived state of the environment to actions to be taken when we are in that particular state. Okay, so this is the policy part. So you can think of it like this, where S is the state space and A is the action space. Next up, we look at reward. So a reward signal basically defines the goal in a reinforcement learning problem. So at each time step, the environment sends some sort of a signal or some sort of some sort of an evaluation metric to the reinforcement learning agent by means of a scalar reward. Okay, so the agent's objective here is to maximize the total reward it receives over the long run. So sometimes it might happen that whenever you are executing some sort of a task, so at each time step you keep on getting small rewards, you keep getting rewarded, but what we are trying to maximize is not the small scale reward, but rather the uh, reward over the long run. Okay, so we are interested more in the expected uh, reward rather than the immediate reward that we get after taking an action. Okay, so this is for those RL problems where we are immediately rewarded and there is no delayed reward setup. Okay, so this we are looking at an immediate RL problem right now. Next up is a value function. So basically, what we mean by a value function is that the value of a state is basically the total of amount of reward an agent can expect to accumulate over the future. So reward is something that you get uh, on taking an immediate action. Value function is basically the expected reward for that particular state or for that particular action. So value function can be associated with a particular state S or it can be associated with a particular action A. So when we associate value function to an action, we denote it by the letter Q. So Q denotes the value function for uh, the expected reward that the agent is expected to receive on taking action A at state S. And similarly, the value function, when we associate it with a state, we denote it by the letter S. So what we mean by that is that it is the expected reward that the agent is expected to receive when it's in state S. Okay, so there's a subtle difference over when we move in with when we move ahead in the course, you will be clearer with the definitions of the value function. So this is just a broad overlook. Okay, so while rewards determine the immediate desirability, the values indicate the long-term desirability of the state. Okay, so reward is something which is immediate, while the value function is something which has a long-term view. Okay. Next up is a model. So model is basically something that mimics the behavior of the environment. You can think of it as the system dynamics. Okay, so it's like let's say you have some sort of a system that gives you a mapping from state S1 to state S2 by means of an action. Okay. So it allows the inferences to be made about how the environment will behave. So given a state and given an action, the model might predict the next state and the next reward. So given state S and action A, you can actually predict state S prime with a certain probability along with the expected reward. So this is when we have the model available with us. Okay. So typically what happens is if we have a model which is available with us, so then it's just a problem of optimizing the MDP that is available, that is provided to us. But typically in reinforcement learning problems, we usually don't have access to the model. Okay, so the agent is expected to kind of approximate the system dynamics by means of repeated interaction. So this kind of splits the class of RL problems into two different types. Okay, so one is a model based RL problem and the second is a model free RL problem. Okay, so this is I shouldn't discuss more on that right now. It's just a broad overview of what RL is all about. I'm just speaking stuff and jumping ahead.
Manav, just one question. Under the value function head, the first point,
Yeah.
it states that the amount of reward an agent can expect to accumulate over the future starting from that state.
Yeah.
Could you please elaborate a bit more on this statement?
Okay. So imagine you have a start state and you have a goal state. Okay. So if you are at the start state and you take one, okay, let me write. You take S2, S3, and eventually you reach the final state, which is G. Okay. So let's take this state into account. Okay. Is there a lag? Okay, I think it's clear. So let's say I'm looking at state S0. Okay. So the first action that I take will lead me to state S1. This need not necessarily be the case, but let's assume that for the
The
state.
sound is not clear.
Okay. So I'm saying that let's say we take some particular action which leads me to state S1. Okay. Now taking action A gives me some reward R1. Okay. So the next time I'm in state S0 again and I take action A1, I again go to some other state, but from here I get reward R2. So let's say I go to state S2 from here. So I get reward R2. So some particular action will uh, result me in going to state S3, which gives me a reward R3. Okay. So when I'm at state S0 and when I take different actions, I get different rewards, which is sampled from sort of a distribution. So this small r is basically the reward part, but when we average or accumulate all of it together, that is called as the value function. So again, reading the statement, value of a state is basically the total amount of reward an agent can expect to accumulate over the future from that is the expected reward that particular. Okay. I hope I was clear.
Yeah, clear. Right. Thanks.
Okay. Yeah. So next up, one basic intuition when we look at reinforcement learning. So this is an important concept that sort of constitutes the crux or the basics of reinforcement learning. So what it tells me is that the prediction about the goal state that I make at time t plus 1 should be necessarily better than the prediction that I make about state goal state s at time t. Okay, so let me draw this maybe. So So let's say I have goal state G, which I want to reach to. So if I'm at state t plus 1, or if I'm at state some particular state at time t plus 1, so the prediction that the task will be completed or I'll reach the goal, there is with higher confidence I can say that I can reach the goal compared to when I'm at state t. Okay. So this is the idea of temporal difference. So think of it, maybe look at the tic-tac-toe kind of an example. So if I split it open like a graph tree structure, okay. So we have a starting position and we have the end position, okay. So when I'm at state G, so G is the end position. When I reach state G, I basically end up winning the game. So the prediction that I make at state F and the prediction that I make at state E, where do you think I'll be more confident? It's at state F, right? So because I only need to take one more step to reach the end state, compared to state E, where I have to take two more states. Okay, so there is a lot of variability that comes into picture over here. So the uncertainty is more when I'm farther away from the goal from a temporal standpoint. So the closer I reach to the goal, the better chance I have to predict the success rate over here, right? So you think of it like again, if you look at the game again at the example of tic tac toe. So given state F, how many times I end up winning the game, which is reaching state G, and how many times I end up not winning the game. Okay. So if you play games multiple number of times, starting from state F, so you might say, okay, from here I have let's say 90-95% chance of winning the game. Okay. Similarly, if you go to state E, the probability sort of decreases. Okay. So now let's say you are 80% confident of winning the game compared to the starting position where the prediction is more or less 50-50. Okay. So this is the basic idea behind temporal difference method. Now, again, what happens is, suppose you here end up making some sort of a move which helped you win the game in the last iteration. Okay. So, is it like I keep on playing the same set of move again and again in the hope that because I won the last time, I make no improvement and keep on following a particular trajectory. So here, let's say here, A, B, C, D, E, F, G is a trajectory, okay, which resulted in me winning the game, okay. But let's say next time what happens is if I reach state C, because this is a two-player game. Okay, so the opponent makes a move which results in me not reaching state D but some other state. Okay, so here do I continue making the same move or do I like try something different? Okay, so accounts is a yeah, you'll get the recording of this session. So this will be uploaded on YouTube, and plus, if you go to the NPTEL Swayam portal homepage, so there will be a small box where you can find the entire recording session. Okay. Yeah. So the dilemma comes up is that do I keep continue do I continue to make the winning move again and again, or do I try something new? Okay. So maybe this is not a good example because tic-tac-toe is a small game. Okay, so the number of states are 2 power 9. Okay, so there are a total of 512 states that or 512 different combinations that can happen. Okay, so let's say if we move to something more complicated like a game of chess. Okay, so because something worked in the previous time, you ended up winning the game, but with some low reward. Okay, okay, maybe I should skip this example because I'm moving towards the exploration exploitation problem. So maybe this is not a good example. Okay, I'll come up with some better example. Yeah. So again, look at the restaurant example. Okay. So it's like if you go to restaurant one. So initially, for all the restaurants, your knowledge is zero. You have no idea which restaurant is better, what kind of food they serve. Let's say you go to restaurant one, you eat the food, you get some positive reward. Okay. So you know that restaurant one right now is better than all the unknown restaurants that I have not visited so far. Now the question is, in this on the second day, do you again end up going to restaurant one and keep doing it till perpetuity, or do you at some point try to explore restaurant two, restaurant three, restaurant four, and different part? It might happen that the food at restaurant two is better than restaurant one, but because I was initially biased to select restaurant one, and because I got some satisfaction. I got some sort of a known reward. I know that this reward is better, so I ended up not exploring the other restaurants. Or we look at the RL problem. I ended up not exploring the uh, other available states in the state space. Okay, so this is a problem known as the exploration exploitation dilemma. Uh, yeah, so it's like. If you remember, there was a story we used to hear in the childhood. So one farmer had a hen who used to lay a golden egg. Okay, so after the end of every 2 weeks, the hen kept laying a golden egg. So the farmer used to take that egg and sell it in the market, and he quickly grew very rich. Now, after some time, the farmer thought maybe hen is laying golden eggs. It might be a possibility if I kill the hen. So inside the hen, I might find a lot of golden eggs. So I might end up growing richer quickly. Okay. So that's like some sort of an exploratory behavior. Okay. So the exploitation part is something that I told before, that the hen keeps on giving a golden egg after every 2 weeks. So the exploration part is if I kill the hen, will I end up getting the entire stock of the eggs available? Okay. So that's where the dilemma comes in. So exploration consists of not making the decision that seems to be optimal, betting on the fact that the observed data are not sufficient to identify the best option. So this more risky approach can sometimes lead to poor decisions, but also makes it possible to discover better ones. Okay, so this is the exploration part. Second is the exploitation part. So exploitation consists of taking decisions that are assumed to be optimal with respect to the data observed so far. So this is some sort of a safe approach that tries to avoid bad decisions as much as possible, but also prevents from discovering potential better decisions. Okay. So if you can think of exploration is like having some sort of a long-term view, and exploitation is having some sort of a short short view. Okay. So to deal with that, towards the end of week one, professor introduced the bandit problem. So the bandit problem is basically similar to the slot machine. So if you go to a casino, so there is a slot machine, you pull a lever, and if a certain combination is received, you end up getting a reward. Okay. So if I have n such slots machines or n such bandits, each of the each of the bandit corres- okay, so each bandit having one arm, and a pull of an arm corresponds to the user getting some reward. Okay, so so this is a very simplistic kind of a problem. This problem comes under the domain of immediate RL problem. So when we look at immediate reinforcement learning problem, maybe I should start writing. So immediate actions gets immediate rewards. Okay. First point. And second point is that there is no notion of a state space in immediate RL. So we typically don't end up maintaining a history of all the arms that have been pulled so far if we are looking at the bandit problem. So it's like each arm pull is independent. It's similar to a coin toss. Okay. So if you are tossing a coin two times, so on the second toss, the result of the first toss don't matter after the first toss is done. Okay. So it's like immediate action gets an immediate reward. There is no notion of a state space. So at time t, action A results in reward RT. Okay, and typically this RT is not something deterministic, but rather this is a distribution. Okay, so this reward is a distribution. Okay, so this is known as the reward distribution. Okay, and here we introduce something known as Q star A. So here Q star A corresponds to the true expected payoff. Okay. So here Q star A is basically the Q is the true expected payoff. Now can someone tell me what do we mean by Q star A star?
True expected payoff of optimal arm.
Yes, that's correct. So it's true expected reward of optimal arm. So you just keep this notation in mind because this will keep coming up in the coming weeks. So it's better to get the notation clear. Small q always denotes the true expected payoff. Okay. When I say capital Q of A, what do I mean by that? Any idea? I think I saw some questions people had asked in the discussion forum. So they were confused between small q and capital Q. So small q is the expected payoff. Okay. Q star is the true expected payoff. Q star A star is the expected payoff for the optimal arm. So here capital Q is always the estimated reward. This is something that we are estimating. We want capital Q to be as close as possible to small q. Okay. It's fine, right? So capital Q is an estimate, is something that we are trying to approximate and reach as close as possible to small q star A. Okay. So I'll quickly just explain the last part of week one on bandit optimalities. So what is the bandit problem here? It's similar to the casino slot machine. Okay. For the multi-arm bandit, there will be K such arms. Okay. So this is known as the K armed bandit problem. So this bandit problem is a very simplistic kind of an immediate RL problem. So this problem is typically used to give theoretical guarantees on the exploration exploitation dilemma. Okay. So what we're trying to do is we are trying to understand uh, how to deal with exploration and exploitation when we are dealt with an immediate RL setup. So the bandit problem is a simplistic problem wherein you have multiple slot machines. You pull an arm, you get a reward. That reward is sampled from a distribution which is set by the casino owner. Okay. So you go into a casino, there are multiple slot machines. Each slot machine has a distribution of rewards. So you pull a lever, you get some reward. Pull another lever, get another uh, other reward, and so on. So eventually, your goal is basically to try to end up getting more reward in less number of arm pulls. Okay, because for pulling each arm, you are also paying some fee. Okay, so this is the basic bandit problem. So the bandit optimality solution. Okay, they typically try to answer three things. Okay, first thing is known as asymptotic correctness. Second thing is the regret optimality, and third is the pack optimality. Okay, so if you have watched the lectures, can someone tell me what uh, we mean by the asymptotic correctness in a bandit problem?
That after infinite time we will be able to find the optimal arm.
Correct. So there is a asymptotic guarantee that if we sample enough number of time all the arms, So asymptotically, we'll reach to the best arm. So this is what we mean by the asymptotic correctness. Okay, regret optimality, anyone?
Like we try to minimize the regret we
What
have.
is regret?
Like like regret is the cumulative addition of all the times we could have chosen the optimal arm, but we didn't.
Yeah. So regret optimality starts off with the notion, let if we knew the optimal arm, so if we knew Q star A star from the beginning, from the very first arm pull, if we knew what was the best possible arm, okay, we don't do any sort of exploration, any sort of exploitation. If we do that, what reward we will get? Or otherwise, when we start pulling the arm, so after some trial and error, we end up reaching close to the Q star A star over here. Okay. So the difference on in the reward on knowing the true expected reward from the beginning and knowing the true expected reward when we start from time t with the exploitation. So this small region, yeah, right like this. Okay, so this small region here is called the zone of regret. Okay. So what do you think regret optimality aims to improve upon? So when we are looking at regret optimality, what is it that we are trying to improve on, or what is it we are trying to maximize or minimize? Any idea?
Reduce the area of this zone.
Yeah, so area of this curve is from a graph perspective, but from an RL perspective, what is it that we are trying to maximize or minimize?
We're trying to minimize regret.
Or you can say it's the optimality for convergence time.
Yes.
Okay, so regret optimality basically deals with convergence. The We want to basically try to minimize the convergence time. But again, what happens if I abruptly minimize the convergence time? It's like I behave greedily and I keep on taking the best possible action from the first stage itself.
Like we will we will reach the slope zero soon, but it would not be closer to the optimal line we have.
Yes, yes, that's correct. So you will have a smaller area. You will your slope will be I mean, the rise will be faster, but then you might not end up reaching to the optimal arc. Okay, so that is some sort of a payoff that we deal with when we work with the regret optimality. Okay, fine. Okay, last one, that optimality. Any idea
Yeah, like
what
after
that
n
optimality?
steps, we have a probability delta that the reward we are getting is epsilon times closer to the optimal reward.
Epsilon times or
Sorry,
epsilon distance.
yeah, like the difference to the optimal reward and the reward we are getting is epsilon.
So, given a variable epsilon and given a variable delta, so my epsilon delta, uh, so my epsilon delta pack basically gives me the probability that Q star of A is greater than equal to Q star of A star minus epsilon, and this probability is necessarily greater than 1 minus delta. So it's basically telling me the probability that I'm approximately close to Q star A star. Okay, so if I were to draw it, okay, so this is my Q star A star line. Okay, so can I put my Q star A here? Is it possible?
No, it should be below that line
Yeah. Why?
because Q star A star is the maximum possible reward we can get.
Yes, it's the optimal. It's the max. It's the expected reward for the optimal arm. So any arm which is non-optimal has to have a reward or has to have a payoff which is below that. Okay. So if I draw a small band here, okay. So the width of this band is epsilon. Okay. So basically, it gives me the probability that my Q star of A should lie inside this region. Okay. So I need to be epsilon distance closer to Q star A star. So this is Q star A. So this Q star A needs to be within the epsilon band of Q star A star. And given any epsilon, given any delta, what I'm trying to do is I am trying to minimize the number of arm pulls. Okay. Because if I pull infinite arms, I'll eventually reach this guarantee. I'll eventually reach the epsilon delta pack guarantee. Okay. So here the aim is minimize n, where n is the arm pulls or the iterations to reach your epsilon delta PS. Epsilon delta PS. Okay, it's clear, right? Okay, so we look at value function based methods. Like I said, QT. What is QT? Basically, attach the estimate to action, and in VT, I attach estimate to state. So, estimate of what? What am I estimating?
Reward.
Not the reward. It's the expected reward. Okay. So since we are looking at the immediate arrow problem, okay, we are looking at the bandit problem. So we won't come up with v v of t, okay, because this is usually associated with state, and since there is no notion of state in a bandit problem, we are only looking at the q function. Okay, so q is basically a value function which is defined as okay. So this is basically an estimate for q star. Qt is basically an average of all the rewards on taking action A. So here A is this corresponds to arm A. Okay, so here action is basically an arm pull. So on pulling arm A, if I pull arm A n number of times, whatever rewards I get, I average that, and whatever estimate that I have is an estimate for Q star. It's the estimate of the expected reward that I get on pulling arm A. Okay, so this value function, this value functions are typically evaluation methods. Okay, you use a value function typically evaluate the strength of the arm pull or the strength of the actions. Okay, so once you have all the value functions, how do you select the best action? So the way you do that is basically you take the argmax over all the action A of qt of A, and that gives me the optimal arm A, right? So did I write it correctly or did I make a mistake? The last line. So am I right in writing this? My A star is basically argmax of A, qt of A.
Yeah, it looks correct.
Uh, the actually is not correct in all cases because if the goal is basically if it is deterministic, then it is correct. Okay, so if each arm pull gives me a deterministic reward, so if I pull the arm one two times, I'll end up getting the same reward, and eventually my arm max of A gives me A star. But in the bandit setup, actually no, this is not correct. This is not correct. This would have been correct if I would have taken argmax of Q star A. Okay, so this is incorrect. You get the difference?
But QT is an estimate for Q star, right?
Exactly. So this is an estimate, but you don't know how close you are, right, to that estimate. What
But
if I have because this is something that you're doing sequentially, right? So let's say you pull arm one time, you get some QT estimate, you select the next action. If so, this is a purely exploitative strategy. This thing is a pure exploitation. So based on whatever QT that you have, you greedily select the next best action. Okay. So this is pure exploitation process. So this need not always result in me getting A star. Correct? See, this QT is a function of T, right? With time T, when with increase in time T, my QT
but
also
like
keeps on evolving.
our aim is to get the QT as close to the Q star.
That is the eventual aim. Okay. So if T tends to infinity, then maybe I can say that my QT is close enough to Q star of A, small Q star of A.
Yes.
Okay.
Yeah.
So there is this subtle difference that you need to keep in mind. My A star is always argmax of Q star of A. Since this is an estimate, I cannot claim the argmax of that to be the A star. Okay. Because it's still an estimate. We want it to be as close as possible to the true expected reward, but at the end of the day, it's still an estimate. Okay. With more number of samples, maybe I can say with more confidence that the arm that I've selected is the optimal arm. That's the max I can do. Correct?
Yes.
Okay, so we looked at a purely exploitative strategy wherein for each at each time instance we directly take the argmax of the known QT at that time instance and pull the next arm, update the QT and so on. Okay. So if I want to do some sort of an exploration, so there were two strategies which were discussed in the lectures. One was the epsilon greedy, and the other was the softmax. Okay, I'll quickly write down what happens in epsilon greedy. So you are basically greedy with probability 1 minus epsilon. With probability 1 minus epsilon, you select the greedy action. And with the remaining small epsilon probability, you select a random action. Correct. So this is the epsilon greedy strategy. What happens in softmax is that the probability of action of selecting action A is basically exp of A divided by beta upon 1 to 1. slash beta. Okay, so my question to you is, what is the fundamental difference between the epsilon greedy strategy and the softmax strategy? So here my beta is the temperature parameter. Okay. Okay, so I'll just quickly explain the epsilon greedy and the softmax for those of you who haven't yet watched the week one lecture. So what happens in epsilon greedy is we don't always select argmax of qt. We select argmax of qt with probability 1 minus epsilon. So with probability 1 minus epsilon, we do argmax A of qt of A. Okay. And with probability epsilon, we sample uniformly from A. Okay. So epsilon here is some small number, some small percentage. So for the maximum number of iterations, we behave greedily. But for some small epsilon probability, we select uniformly from the action space. So here capital A is the action space. And based on that, we learn the optimal arm. Okay. In softmax, what happens is instead of doing the epsilon greedy part, we are relative strength of the comes into account. Okay. So you understand. So here the probability is basically dependent on the probability remaining arm. So the probability of selecting arm A is sort of relative to all the other available arms in the entire multi-arm bandit problem. Right. So think of it like this. So if there is a small difference between two arms, okay, small difference between two arms, my epsilon greedy strategy will always try to give more preference on selecting the arm which is slightly higher because mathematically it is satisfying my argmax of A. But in the softmax part, the probability of selecting arm those two close arms would be more or less similar. Okay. So here, if some particular actions gives me negative rewards or are simply bad, I don't want to end up wasting time in selecting those arms again and again during my exploratory phase. This might happen in my epsilon greedy part. What I'm doing is, apart from the best possible arm, the entire action space I'm selecting a random action. So it might happen really bad action. I can end up sampling that. Okay. So there is some sort of a randomness involved when we look at the epsilon greedy. Okay. But here in the softmax part, it's more algorithmic in nature, right? The probability of selecting one arm over the other. The probability updation is more algorithmic rather than entirely random, as was the case in the epsilon greedy. So here the beta term is basically a temperature parameter. So based on the tuning of the beta parameter, the way in which try to do the exploration. Okay. So if beta is very high, if beta is very high, then the probability of selecting each action is more or less uniform. Do you agree with that?
Yeah.
As beta tends to go higher and higher, the probability of selecting arm A becomes closer to 1 by n, where n is the total number of arms. Okay. And similarly, as we reduce beta, as beta goes closer and closer to 0, when beta is very close to 0, the arm that I'm selecting is again selecting the max arm. As beta goes close to 0, the arm selection is more or less greedy. Do you agree with that?
Can you explain this again? Like how?
So when beta is close to 0, what happens to the numerator?
Beta is
Sorry?
beta is closer to that is e to the power infinity, right?
Let's have three arms. Okay. So let's say I have three arms A, B, C. Okay. And now this is the probability distribution for arm A, B, C. All of them sum up to 1. Okay. So this is the estimate that I have. This is my QT values for each arm. So my y-axis corresponds to the QT and the x-axis corresponds to the arm, right? So my E of QA Okay, so this is the probability of selecting army. Now tell me, what happens when beta goes closer to 0? You might see that as and when beta goes closer and closer to 0, so the arm which has the maximum q value, which has the maximum value function, ends up dominating over the other part. So here, let's say A has the highest payoff, okay, till now. So my E of QA by B will end up dominating these two terms, right? So my E of QA slash B and this extra term would be more or less approximately equal to E of QA by beta. Do you agree with that? This is the dominating term here when beta is very, very small.
Yes.
So if beta is very small, it scales up QA by a large factor. It scales of QB and QC by relatively smaller factor. But since the scale up is so huge, my first term is much larger than my second and the third term. So eventually, what I end up getting is
Probability of the
approximately 1. Okay.
yes.
So what it means is I ended up selecting the arm with the maximum Q value. So this is basically the magic of tuning the beta parameter. If beta is very, very high, Uh, if beta is very high, it's almost as equivalent as selecting the arm pull uniformly. And if beta is very, very low, we are moving from the soft max to the max selection. Okay. So you understand that why this is named soft max. We are not selecting the max, we are selecting the softer version of the max based on the beta parameter. Okay. Yeah. Okay. So I think it's 7:30 now. Maybe we can discuss the week one practice assignment and also look at the week zero practice assignment. So if you have any doubts, you can ask me. So we'll try solving it together. So we start with week one. There were five practice questions. First question is, which of the best suits the notion of regression in a standard multi-arm bandit problem? What's the answer? Again, what is regret? What is uh, what do we mean by regret?
It's the third option.
Yes. So regret is basically the difference. If we knew the optimal arm from the beginning and the reward that we get by our solution method. So it's the third option. Okay. Second part. So at the beginning of the class, we discussed the credit assignment problem. Okay. So it's like if I have a sequence of micro actions in order to receive a reward. So credit assignment is which action resulted in me getting closer to the reward, and how do we reward them equally, or how do we assign credit to each micro action. So which of the following is the reason for the credit assignment problem in RL?
Delay.
Correct. So in the delayed reward setting, the problem of credit assignment usually comes up. Next up, there are three statements. Which of the above is or are correct? So always keeping epsilon as constant is a good approach. So this is related to the epsilon greedy approach. So always keeping epsilon is a good approach.
In case of stationary, it is not,
We
because
are correct right now dealing with the stationary part only.
yes,
Stationary stability.
eventually we will be very close to the optimal arm, like what we have.
You will be very
In
close to the
that
optimal
case, we
arm.
do not need to do exploration.
Sorry?
So when we have gotten, like when we have the optimal arm, we don't need to do exploration anymore.
Correct.
So we need
So
to reduce
keeping
the,
epsilon constant won't allow that, right?
yes.
So keeping epsilon constant means there is always an epsilon probability, even after getting the optimal arm, I still end up doing unnecessary exploration. So option one is not correct. Second option is large values of epsilon will lead to unnecessarily exploration in the long run.
Yes, it's true.
Yeah, this is correct. And third is cooling down epsilon too fast is problematic as it cannot guarantee correctness in the value estimate.
Yeah, again true.
Yeah. So typically you start with epsilon and over time you slowly decrease the epsilon because initially when you start a task, you want to explore more. But after, let's say, some time steps t, you want to favor exploitation more than the exploration. So this epsilon, keeping epsilon constant will always lead to a constant exploration, even at infinite time of the at the infinite iteration. So that's why we typically try to decrease the epsilon, but cooling it too fast is problematic because then that does not result in sufficient exploration. Okay, so here option here option D is correct, right? So here this is a numerical problem. So the for a standard multi-arm binding problem, the probability of picking an action using softmax policy is given by this formula. Now assuming all the q values given, what is the probability that action 2 is selected? Use beta as 0.5. So action A2, right? So the probability it is equal to A2 is equal to e to the power 0.5 divided by 0.5 upon e to the this is 1 by zero point 0.5. This is zero point 0.5 by zero point 0.5. This should be point, two. So this is zero point 0.2 by zero point 0.5 plus e zero point 0.5 by zero point 0.5 plus a minus 1 by zero point 0.5. So this is a pure calculation exercise. So if you solve this question, the answer you get is
Like, will we have similar questions in the final exam? Because it would require a calculator to solve this.
uh, typically in your final exam you will have an on-screen calculator. So there is a possibility such questions might come up.
Okay.
Okay. So the correct answer here is
0.23.
yep. Again, a question of which of the above statements are correct. The rewards are obtained at a fixed time after taking an action.
Not always true. Like, there's not a fixed time.
Yep. Reinforcement learning is neither supervised nor unsupervised.
True.
This is true. Two RL agents can learn by playing against each other.
True.
This is true. This was demonstrated in several classical board games. Always selecting action with maximum reward will automatically maximize the winning probability in a game.
False.
This is false because there is no scope of exploration. So, okay, so this completes the entire week one session section of what I had in my mind to cover. If you have any other questions, you might ask. Otherwise, I have the week zero practice assignments. If you have any questions, any difficulty in the week zero practice assignment, so this basically tests your knowledge on linear algebra. So you might want to stay back and I'll discuss the 10 questions quickly. Okay, so the first question is slightly trickier. I would say out of the
Another
10
question
questions,
regarding the exam. So, we will be having question of probability and linear algebra in the exam.
mm, probability in the sense
Like
something
the
similar to
questions
this.
we have in this practice assignment.
Questions you have in a
In
week
this
zero
practice,
assignment.
yes.
Might be, might not be. So
Because I
I
was
don't
able
know.
to solve them, but only after I googled the formulas. So I don't remember the formula.
So these are all like conceptual kind of questions. I don't think these will come up in an RL exam, but you never know. Some questions might pop up randomly. Okay. So it's better to be prepared. Okay, so how many of you had difficulty in solving this question? Or if someone can tell me the approach on how to solve this question.
So I tried to calculate like tried to calculate by taking the minimum values and to get the lower bound and the maximum values to get the upper bound.
Yeah, but how do you start? What is the starting point?
So like the probability of A union B given C can be written as probability of A union B intersection C, like using the Bayesian formula. So I opened it and then I tried to find the minimum value of A intersection C.
Like this?
Yeah, and then we can open it A intersection C union B intersection C.
Mhm. So you saw what I did?
Yes.
So basically, I opened up the intersection by the intersection union formula. So I expand it like this. This given quantity becomes 1 because these are the three sets which are given to us. Okay. So this is the assumption that I make that this constitutes the entire universe because no other additional information is given. Okay. So this quantity becomes 1. Fine. Now, if I just open up A union B, so I can write it as P of A plus P of B plus P of C minus A intersection B minus 1 divided by P of C. Correct?
Yes.
Now I just plug in whatever values I know. I eventually end up with 1.1 minus P of A intersection B divided by zero point 0.9. Okay. Now I have to find out the minimum value of A intersection B and the maximum value of A intersection B. Now, if I want to find out the maximum value of A intersection B, so can I say something like if this is set B, my set A is completely inside set A. So this will give me the maximum possible intersection, right?
Yes.
So if in the case that set A is completely inside set B, so the maximum possible intersection that I can get is zero point 0.5.
Yes.
So my min value, for my min value, I take the maximum possible value for the A intersection B, which ends up giving me 1.1 minus zero point 0.5 divided by zero point 0.9, which is 2 by 3. This is the min value. Now for the max value, I want to minimize the intersection B. What is the lowest value for A intersection B?
Point 2.
Why? Why can it
Because
not be
A
0?
union B is equal to P of A plus P of B minus P of intersection.
Okay, and what is A intersection B?
And A intersection, like union cannot be greater than 1. So 1 equal to zero point 0.5 plus zero point 0.7 minus intersection. That would
Yes,
give me
that's
2.
correct. Ref got it, right? What he said. So my P of A intersection B can never be 0 because my P of A and P of B, which is zero point 0.5 and zero point 0.7, is greater than 1. Okay. So my intersection term can never be 0. there needs to be some sort of overlap, and the minimum possible overlap here would be zero point 0.2. Okay, because the union can never be greater than 1. So for the max value, I take 1.1 minus zero point 0.2 divided by zero point 0.9, giving me the value of 1. So this is the correct option. Any doubts in this question? Or should I move ahead?
Hello, hi Manav.
Right, right.
Uh, Actually, I just want to ask some another information. Actually, I just want to take. I'm sorry, I'm disturbing between the question.
Yeah, it's fine.
Uh, how I will means able to access this recorded lecture?
So after the lecture is completed, this will be uploaded to YouTube. So the NPTEL team will share this recorded lecture. So if you open the web page for the Swayam portal, so you see week 0, week 1, and below that you have download videos, all those stuff, right?
Yes.
So below that, there will be another section known as problem solving session. So if you click on that part, you will have access to all the recorded lectures so far that we TAs are covering. What professor is covering is already there in week 1, week 2.
Yes, yes. And do professor can we connect with professors also directly?
Mm,
Means
you can try emailing him, but since I am not associated with IIT Madras, so I can't guarantee that. You can try, obviously, from your end. You can try emailing him if you have any questions.
okay. Thank you.
Okay, cool. Okay, so this question is fairly simple. So you want to find the variance for the random variable x when x follows this particular distribution. Simple formula for variance is e of x squared minus e of x the whole squared. Correct? So now I want to find e of expectation of x square. My expectation of x square is x square fx dx the whole integral. Okay. So since this integral is from 0 to 1, I'll just write it 0 to 1. 3 comes outside. X square goes as it is. I'll just open the bracket term. So it's 1 plus 4x squared minus 4x dx. Correct? So this gives me, so x square integration is x cubed by 3. Because this is from 0 to 1, so this is 1 by 3 plus 4 by 5 minus 2. It's correct, right? What I've done? That becomes 5 plus 12 by 15. 17 by 15 minus 2. No, no, no. This is x power 3. 4x power 3 becomes 4. becomes 1x, right? So eventually what we have is 3 times 2 by 15, which is 2 by 5. Okay. And similarly, my expectation of x is x of x dx, which is 3 times 0 to 1 dx. So this is 1 by 2 plus minus x square. X square is 4 by 3. Right. So what you get end up getting is 3 by 2 minus 4 by 3. 1 by 2. No, it's 1 by 6, which is 1 by 2. So now I have expectation of x square. I have expectation of x. I simply plug in the equation. So this is 2 by 5 minus 1 by 2 the whole square, which is 1 by 4. So the final answer is 3 by 20, which is this option. Correct. Okay, so this is a true false kind of a question. Which of the following is false? Quickly, anyone?
Last option.
Yep, that's correct. Why? Because expectation of y given x can be written as
Expectation of y.
expectation of y intersection x divided by expectation of x, right? If I expand that conditional expectation formula, right? Since these are independent, so this is expectation of y times expectation of x divided by expectation of x, which eventually gives me expectation of y. Okay, that means my y is not conditioned on x because they are independent random variables. So the fourth option is incorrect. Rest all are true. Next is which of the following is not a valid norm function?
The minimum one.
Yes. So the way you approach this problem is for something to be a valid norm function, it should follow the triangle inequality. Okay. So the triangle inequality is f of x plus f of y should be greater than or equal to f of x plus y. Okay. This is the triangle inequality. So you plug in each of the given norm functions, see which of them don't follow the norm function, and that would not be a valid norm function. So in the last part, my min I of xi plus min I of yi, if I compare it to min of xi plus yi, so this is less than equal to this quantity. Do you agree with this? Rest everything else, if you plug in, that will always be greater than equal to uh, f of x plus y, but only in this case, this is less than equal to. So this is the correct option. Okay, which of this is false for a matrix M?
Third.
So the third option is the correct answer because Trace of a matrix is always equal to the sum of its eigenvalue. Determinant is always product of eigenvalue. And rank of matrix M is equal to the number of non-zero eigenvalues. So these are all as per the definition. So the real eigenvalues of M are distinct, need not always be true. There might be repeating real eigenvalues as well. Okay, this one. Let A be non-singular square with eigenvalue lambda 1 for vector x, eigenvector x, and B be square matrix with eigenvalue lambda 2 for eigenvector x. What is the eigenvalue for matrix A inverse BK for eigenvector x? Okay, so we know that A of x is lambda 1x and B of x is lambda 2x. Okay, now I want to find the eigenvalues for A inverse BK A. So if I operate this on the eigenvector x, so when A acts on x, I end up getting lambda 1 and remaining A inverse B power k of x. Okay. Now when B of k operates on x, so if Bx gives me lambda 2x, so the kth power of B will give me that power of the eigenvalue as well. So it's lambda 1 times lambda 2 power k A inverse of x. Okay, this is the remaining quantity. So I have lambda 1, lambda 2 power k. A inverse of x is, since A of x gives me lambda 1 of x, so A inverse of x will give me the inverse of the eigenvalue. So this will be lambda 1 inverse. Okay, so this 2 cancels out. You end up getting lambda 2 power k. So this is the correct option. Okay, next up, let x1, x2 be two independent random variables with given mean and given variance. What is the value of e x1 minus x2 the whole square? I'll just quickly show this. This can be written as x1 squared plus x2 squared minus twice of x1 x2. Okay, because expectation is a linear operator, so I just write it like this: e of x2 the whole square minus twice of e of x1 and e of x2. Okay, so my e of x1 and e of x2 are the means. Okay, and my e of x1 square. So e of, or how we define variance. My variance of x is basically e of x square minus e of x the whole square, right? So I can write my e of x squared as variance of x plus mean of x the whole square. Okay, so this is how I define my e of x square. Uh, Not the whole square. This goes inside the bracket. Okay, so here I just substitute. So e of x1 is variance of x1 plus mean squared. So which is 5 plus 1 square is 6 plus 8 plus 4 square is 8 plus 16, which is 24. And this is 2 times 1 into 4, which is minus 8. Final answer is 22. Okay. Okay, so you're playing a game in which you have to choose one bag. Okay, so there are two bags here. This is bag one. This is bag two. So inside bag one, there are 5 red balls, 4 green balls, 4 yellow balls, and the payoffs are 50, 25, minus 30, respectively. Inside bag two, 4 red balls, 7 green balls, and 5 yellow balls with payoffs 30, 30, minus 20. So now which bag do you choose to maximize the total number of points? Okay, so I just need to find out the expected reward on selecting bag one. So which is the probability of selecting a red ball times the reward on selecting a red ball. So probability of selecting red ball is 5 by 13 times 50, plus similarly for the green and the yellow ball, it's 4 by 13 times 25 plus 4 by 13 into minus 30. Okay. So if you do all the calculations, you end up getting 230 upon 13. Okay, you can check it. Similarly, I compute the expectation on selecting bag 2. So this is 475. So 16. This is 4 by 16 into 30 plus 7 by 16 into 30 plus 5 by 16 into minus 20. Again, if you do the math, you end up getting 230 by 16. So this is the higher value. So you're better off selecting bag 1 compared to bag 2. Okay. Two more questions to go. So a stick of length L is broken into two parts, chosen uniformly randomly. What is the length of that? Okay, just a second. Stick of length L, smaller piece length. The length of between 0 and L by 2, correct? Because anything beyond L length L by 2, it no longer becomes remains the smaller piece, it becomes the bigger piece. Okay, so this is the distribution. So the smaller piece length should be between 0 and L by 2. So the average length of the smaller piece is basically telling me to find the mean of this uniform distribution. So I have a distribution X, which is between 0 to L by 2, and this is a uniform distribution. So the mean of a uniform distribution is basically the average of the two extreme ends. This is 0 plus L by 2 by 2, which is L by 4. Lastly, A is a positive. Okay. So when I say something is a positive definite matrix, what it means is that all its items are real and they are positive. Okay. So they are real and the eigenvalue. If V and W are orthogonal eigenvectors of A transpose A, which of the following is true? So if I operate my A transpose of A on V transpose of W, and the thing is A transpose of A, and transpose of W. This is, oh no. So I'm just taking a case. So I have V transpose and I just operate A transpose of A on W matrix and just multiplying it with V transpose. I'm not operating on the A transpose of A. Start with AW orthogonal. So what it means is that A times MW should be equal to, expand this, I get V transpose, A transpose, A, blue, again 0. No, I shouldn't write it 0. Should be, okay, I just take the first case. I just open it up. I get V transpose, A transpose, A, W. Okay. Since W is an eigenvector for A transpose A, so I end up getting some eigenvalue lambda W. I denote it as lambda W. And then I have V transpose W. Okay. And since this quantity is 0, so that means my A operated on eigenvector V and A operated on eigenvector W, they both are orthogonal. So option 1 is correct. If you check the other options, you end up getting 0. Only in the you get R is equal to 0. So this is correct option. So yeah, it's already, I think we by 10 minutes. So thank you for staying so long. Uh, Thank you for attending this lecture. Uh, I'll see you next week, Friday, 6 to
We can just answer one question. Yes, like we have a session tomorrow and day after tomorrow also. So will they be covering the same things or?
that actually is dependent on the individual TA. So they won't, like, we all are conducting each sessions differently. So it might happen that the insights that I provided and the insights the other TA might provide would be different. The set of questions that we cover in the subsequent sessions, be it the coding related session or any other session, it might there might be some overlap, but it won't be exactly the same.
Okay.
Okay. All right. Thank you for attending. Thanks a lot.
Thanks, Mano. So tomorrow also we have the class at the same time, means 6 to 8.
Tomorrow session. Uh, I'll have to see. It's not exactly the same time. Okay, so Saturday
Saturday
it's
it's
3 to 5, 3 to 5, and
and
Sunday
Sunday
5
5
to
to
7.
7.
Okay.
Okay.
So on the Sunday, will you please between 9 to 11 in the morning?
Sunday it's 5 to
Sunday it's
7
5
in
to
the
5 to
evening.
7 evening.
Okay.
And Saturday
And
it's
Saturday
3
it's
to
3
5.
to 5.
Okay. So we will get the link on mobile, just like we get this link for today's session.
Yes, yes. All of the recordings will be made available on the Swine portal itself.
Okay. Thank you, Manav. Thank you so much.
Okay. Thank you. Thank you for attending.